Hi, this is Mr. Sand, and we're going to talk about Hess's Law. Hess's Law is a much more accurate description of the change in enthalpy, which we described before. The reason it's such a more accurate description is because it talks about a molecule decomposing into its constituents at normal standard pressures that we see here on, like, Earth. It's not a kind of idealized average or anything like that. It's like the real day-to-day kind of reactions that are happening. So it gives us a much more accurate description of the change in enthalpy. So I'm going to describe it to you in this kind of strange way. So the great thing that Hess discovered was that if you have, let's say, a reaction going from A to B, and then another reaction going from B to C, and then another reaction going from A to D, if you've got the delta H here, call that delta H1, the change in enthalpy 2, and the change of enthalpy 3, well, then the change of enthalpy from, if you're doing A to D, you can say, it's the delta H1 plus delta H2 plus delta H3. Oh, this should be D, not B, D. So you can figure out what going from A to D really is, even if there are intermediates along the way. And it uses delta H. Oftentimes it has this little zero above it, the standard enthalpies, that are slightly different than what we've been using before for the individual bonds. It's more about a molecule being decomposed into its regular constituents. So you can add up all of these delta H's and you'll get an overall change in enthalpy. If it's a negative change in enthalpy, then it'll be exothermic. So if delta H is negative, that equals exothermic. That means it's giving away energy. If delta H is positive, that equals endothermic. Just like before, but now we have these kinds of little connections here along the way. I like this because I think it makes sense. And it's also, there's lots of like little puzzles along the way that you get to kind of puzzle out. So I'm going to take you through a couple of these puzzles right now. The first one is in your warm-up. It should be pretty easy for you. It's right at the bottom, right over here. So let's take a look at this. It says, what is the enthalpy change, or what's the change in enthalpy in the reaction A goes to D if, here's all the different steps along the way. So this is exactly the same setup as I just said. So what you have to do here is you just have to add up. Since A goes to B, and then B goes to C, and then C goes to D, if you want to find out what A to D is, you just add up all these delta H's. So it's going to be 100 plus negative 800 plus 900. So if you do all of this, this is going to be just 200 kilojoules per mole. It should be. Okay? If you take a look at this one, the next one, the warm-up problem number 2, it's a little bit more difficult. And now we're starting to see a little bit more complexity in the power of Hess's law. So if you go from A to B, or I'm sorry, let's start off with this. If you go from A to 2D, that's what you want. That's your target here. And you're given all of these standard values. Okay, these are calculated in the lab right here. The reactants going to the products. You can see here, I'll just kind of put this out. I'll draw this out on this little white sheet here. So if you've got, you want A going to 2D, that's what you want. That's your goal. So I'll put a rectangle around that. But you've got A going to B, and you've got, as a standard, B going to 2C, and you've got C going to D. And you've got the delta H's for all of these. This one was delta H is 100, and we can just leave out the units for now because it slows things up. This is negative 800, and this delta H is 900. There's a couple things you could do to these equations and then manipulate them, and then you'd have to manipulate this delta H over here. One thing you can do to this equation is you can say, all right, A goes to B. Well, if I want, let's say 2A going to 2B, then I can multiply everything by 2. And that includes this delta H. So if I want 2A going to 2B, that's fine. I just multiply this by 2. So I would say, okay, that would be 2, that would be 2. Then you have to multiply this by 2 as well. And that'll get you the delta H if it's 2A going to 2B. Right? I'm not going to do that right now, but it's just something if we wanted to do. Another thing you can do is you can switch these two terms around. You can say, all right, I don't want an equation going from A to B. Instead, I want an equation going from B to A. Well, it's possible to switch this around. You just have to make sure that you switch the sign over here. This delta H would then be negative 100. All right? Okay, but I'm not going to do that right now. Now I'm going to tell you a strategy. Okay. The strategy I have is to treat these arrows as equal signs and to get the terms that I don't want in my overall equation to be equal amounts on both sides, so that way I can cancel them out. And I want to be left with just 2D on this side, and I want to be left with just A on this side, which means I want to get rid of the B's and I want to get rid of the C's. So right now I've got a B on this side. If I add all these out, that's what would happen. I would get from A, I want to get from A to 2D. So right now I've got a little bit of a problem. I go from A to B, then I go from B to 2C, and then I go from, well, I don't even have 2C, but I've got C going to D. Now you might just say, right, I need to multiply this whole thing by 2 right here, and then I would get the right overall reaction. That's right, but I'm going to do that. So I'm going to multiply this whole thing by 2, and this will be by 2 as well. But I want you to see something. I want you to see that there's some cancellation going on here. I want you to see that B is on this side, and when you're adding all of these up, B is on this side and it's on this side. So that means it's being used up. It's going right into something else. So what I can do is I can cross this off. And 2C is being used up as well. It's going right from 2C into 2D. So our final is going to be 2D. And our initial is going to be A, which is what we want for our overall equation. So this, if we multiply this 900 by 2, which is 1800, and then you add all of these enthalpies up, you're going to get the correct answer. So this is going to be as many kilojoules per mole. Okay, this is all good. Let's get to a hard problem. I'm going to skip over the last one more problem, and I'm going to go to number 4. Number 4 looks like this. It says calculate delta H for the reaction is 4 NH3 in gaseous state plus 5 O2 in the gaseous state goes to 4 NO in the gaseous state plus 6 H2O in the gaseous state. It's all in the gas. So we don't really need to worry about those states of matter right there. So what do we do about this? I'm going to take a quick screenshot of this. I'm going to paste it into the sketchbook right here. So let's do that. You zoom up. Okay, quick. Whoops. Okay.